Hi, hello students. Welcome back to India's most comprehensive online learning platform, BYJU'S Exam Prep. This is Anil Sir, and in this session, I'm going to bring you some important PYQs in which, from the previous years, which have been conducted by the Kanpur IIT. Because you know that in 2023, the GATE exam is going to be conducted by Kanpur IIT. So we just need to understand the pattern of the question that have been given by Kanpur IIT. Already I think we went to one session. In this session, I'm going to bring up a few questions from the Kanpur IIT, especially in computer architecture and organization. Please let me know your presence and just please mark your presence. And once again, let me take the initiative and privilege to welcome all of you guys. Still it is saying that it is 2:18. Just I need to see. Am I audible and visible? Yeah. Am I audible and visible? Please mark your presence. Do we have anybody here? Okay, then fine. So let me start this session. Yeah. The thing is, when we talk about a computer architecture and organization, we had many of the previous year questions solved. I myself just taken a lot of sessions, especially for the PYQs in the past any number of years. Once again, very good afternoon. Yes, good evening. Yeah, let us start a few PYQs, because it is always better to go through the question that have been given from the previous years of the the university or the IIT which is going to conduct the GATE exam. So let us start this session without having any hassle whatsoever. This is all about my teaching experience. Most of you people, you already know. I do have a total of 13 plus years of experience. I taught everywhere in India. For the past 13 plus years, I've been teaching, I've been priming the people in GATE exam. I taught everywhere all across India, including Andaman and Nicobar and Jammu Kashmir. I'm a triple PG holder. I did my MSc in mathematics. I did my MS in information technology, and also I did my MBA. Without wasting any more time, let me take you people into the session straight away. Here it goes, the first question on your screen. Consider CPU with a 4-way set associative cache with 128 lines with a line size of 64 words. The CPU generates 20-bit addresses. The number of bits in tag, line, and the word fields respectively. This question is given in 2007 as is on the screen. The question once again for you guys, that is, consider a CPU with a 4-way set associative cache with 128 lines with a line size of 64 words. The CPU generates 20-bit addresses. The number of bits in tag, line, and the word field respectively. This is the question. Now let us understand how to solve this kind of a question, and we have solved this kind of a question bag full. In previous any number of sessions, we've been solving this kind of a questions, because it does belong to the cache mapping techniques. You know that the cache mapping technique is an important topic in the entire memory. We are going to expect a similar question in the upcoming GATE exam, because the cache mapping technique, no matter whatever, I mean, we may expect a lot of questions from the memory, that too from the cache mapping techniques. We know that, excuse me. Yeah, we know that memory is an important topic, especially memory is a very important topic in which, in the memory, that to cache mapping techniques, no matter what kind of a mapping technique it is, every year we gonna get one question from the mapping techniques. That is a direct mapping technique. It could be a direct mapping technique or an indirect, rather set associative mapping technique or associative mapping technique. Now here we've been asked about a 4-way set associative cache. The 4-way set associative cache is the kind of a cache in which the tag bits will be equal to tag plus 2 and the block bits will be equal to block minus 2. Let me show you how we'll be able to solve this question. Hi Anita. Hi Anita. Very good afternoon. It is 776. She's saying, let me show you how we will be able to solve this. Now let me draw this. A simple way to solve this kind of a questions is just, draw the number of bits for the address. What is the total number of bits of address in? We do have 20 number of bits. The total address bits is equal to 20, right? Then we need to divide these 20 bits into index plus tag. What is index and what is tag? Index is number of bits that are needed to represent the cache memory, and the tag bits are, the remaining bits after we dedicate a few bits to represent the cache memory. So here we should be able to divide these 20 bits into two parts. The first one is index and the second one is tag. Here, let me tell you, we don't need to do any practice whatsoever because everything is clearly given. Here the total number of lines are clearly given. What is the total number of lines? The total number of lines are equal to, according to the question, 128. Now we don't need to even divide index plus tag. Directly we can divide tag and the line and the word field. This is the word field, this is the line field, and this is the tag field. Total is equal to 20. Now we will start from the word field. What is the word field? Word field is equal to the block size. We need to pick out the block size. What is the block size? The block size, according to the question, 64 words. Block size is equal to 64 words. 64 words requires 6 bits. That means that the word field requires 6 bits to represent it. So the word field will have 6 digits and the line field directly has been given. What is the total number of lines? The total number of lines according to the question is equal to 128. 128 requires 7 digits whatsoever. Hi Anita. Yep. 7. So 128, 7. Just deposit these bits here at the line field. 7 plus 6 is equal to 13. And 20 minus 13 is equal to 7. 776 is the correct option. This is the kind of a question that we are actually expecting in the next GATE exam, because no matter what, it could be, do not fall into the trap of the information. Here, what I'm just telling you is, we may get a question from the cache address mapping techniques. It could be a theoretical question, it could be a NIT type. It could be anything, but here you're gonna get a question from the cache mapping techniques. It will be direct mapping, set associative mapping, or associative mapping. Okay, so 776 B is the correct option as you guessed. Now, the next question is, assume that for a certain processor, a read request takes 50 nanoseconds on a cache miss and 5 nanoseconds on a cache hit. Suppose while running a program, it was observed that 80% of the processor's read requests result in a cache hit. The average read access time in nanoseconds is. It is one more important topic in the entire memory, that is average memory access time. Generally, how do we calculate average memory access time? Average memory access time calculation is pretty much simple. It's predominantly simple. That is, if you want to calculate average memory access time, there is a simple logic and simple rule. Average memory access time is equal to H1 T1 plus 1 minus H1 into T1 plus T2. If it is a one level cache, that is H1 T1. Okay, H1 is the hit ratio or a hit rate of level 1 cache. T1, time required to access the level 1 cache. 1 minus H1, that is the miss rate of the level 1 cache. T1 plus T2, that is the time required to access the first level cache and the time required to access the main memory. This is the average memory access time rule for a single level cache. If it is a two level cache, average memory access time is even more simple. Average memory access time for a two level cache is H1 T1 plus 1 minus H1 into T2, 1 minus H1, bigger pardon, 1 minus H1 into H2 into T1 plus T2 plus 1 minus H1 into 1 minus H2 into T1 plus T2 plus T3. This is the rule for 2-level cache. But here, I guess we've been provided with only 1-level cache. Assume for certain processor, a read request takes 50 nanoseconds on a cache miss and 5 nanoseconds on a cache hit. That means that here we are having only a 1-level cache, right? We just having 1-level cache. And we do not need to think about 2nd-level cache because this is unnecessary according to the context of the question. We just need to deposit, we just need to plot the values according to the 1-level cache rule. That is, AMAT for 1-level cache is simply equal to H1, hit rate of the level 1 cache, into T1, access time of the level 1 cache, plus 1 minus H1. That is, miss rate of level 1 cache into T1 plus T2. The access time of level 1 cache plus access time of the main memory. Simply if we can plot the values, I mean, what is H1? H1 is hit rate is where is 80%, right? 0.8. If the hit ratio is 80%, hit rate is equal to 0.8. What is T1? T1 is time required to access the level 1 cache. Time required to access the level 1 cache is equal to 5 nanoseconds as it is given, plus 1 minus H1 is 0.2 because 1 minus 0.8 is equal to 0.2 and T1 plus T2. T1 plus T2 is the time required to access the level 1 cache plus the time required to access the main memory. But according to the context of the question, if you actually can read it carefully, this 50 nanoseconds is the total time taken to access the memory during a cache miss. That means that it includes both the time that has been taken at the level 1 and the time that is going to take in the main memory. This 50 nanoseconds in the simple words is T1 plus T2 according to the question. T1 plus T2 is given in the question. As simple as that. Now 0.2 into 50 nanoseconds. Okay. Now the thing is 0.8 into 5 is equal to 4 plus 0.2 into 50 is equal to 10, which is equal to 14 nanoseconds. So option D is the correct option. Here only one thing that we need to understand in this context is how we got to 0.2 into 50. What I said, when it comes to AMAT, there is the rule that H1, what is H1 here? I will tell you a simple rule here. Let us say this is a level 1 cache. Let us say this is main memory. Here you need to understand that generally CPU comes to what we call the level 1 cache. Let us say cache memory for stage of any information. It doesn't go directly to the main memory. Now, in the case of a miss only, it goes to the main memory, right? But here we need to understand that when CPU goes to this cache memory initially, it is going to it is going to take some time to find whether the information is available at the cache memory or not. Is going to require some time. For an instance, cache memory takes 2 nanoseconds. So initially when the CPU goes to perform a search within the cache memory, obviously it is going to take 2 nanoseconds. Right after which it found out that the cache memory, it did not find the relevant information, the desired information. Then it goes to the main memory. Now the thing is, here the total access time includes memory access time as well as the cache memory access time, right? So during a miss, only it goes to the main memory. That means that we should be able to include the time that has been wasted at the cache memory. So here the thing is, if you actually can read the question, a read request take 50 nanoseconds complete on a cache miss. During a cache miss, total access time is equal to 50 nanoseconds. That means that this 50 nanoseconds include both T1 plus T2. This is the very reason why I directly put there 50 nanoseconds. So this is how we're gonna get to the answer. 14 is the correct option. The next question is on your screen. Consider a non-pipeline processor with a clock rate of 2.5 GHz and an average cycle per instruction of 4. The same processor upgraded to a pipeline processor with a clock speed of 2 GHz. What is the speed up of the new processor? This is a pipelining question. This is a question on the pipelining. The consider a non-pipeline processor with a clock rate of 2.5 GHz. Here we got a non-pipeline processor. The non-pipeline processor speed up is rather, clock rate is equal to 2.5 GHz. Okay. And the average cycles per instruction of 4. That means that every instruction is gonna take 4 cycles, 4 clock cycles. For the execution of a single instruction, this non-pipeline processor just requires 4 clock cycles. The same processor upgraded to the pipeline processor with a clock speed of 2 GHz. Here the thing is, it's been upgraded to 2 GHz. And what is the speed up of the new processor? I guess, some information is being lacking. 4 stages or 5 stages? Let me check it out. The validity of the question here, because I am, there is some data missing in this question according to myself. Let me see this. Consider non-pipeline processor. Non-pipeline processor, 2 GHz. Let me see the question completely. The same processor upgraded to pipeline processor with the 5 stages here, which is missing in the question. Stages of the pipeline processor is being missed here. The stages of pipeline processor is equal to 5. It's been missing, but due to the internal delay, the clock speed is reduced to 2 GHz. And what is the speed up? This is the question here. And now understand that how we'll be able to get the speed up. The speed up is equal to non-pipeline processor time, NPS divided by non-pipeline processor, speed up is non-pipeline processor NPT divided by pipeline processor's time. Now, we need to calculate the non-pipeline processor time. Let us take only one instruction. That is, for one instruction, it will take 4 clock cycles. 4 clock cycles into 1 by 2.5. Because this 1 by 2.5 is the clock cycle time, and 4 clock cycles, and each clock cycle is equal to 1 by 2.5. When it comes to the pipeline processor, of course, we know that without no delay, each and every instruction will only take 1 clock cycle. In the pipeline processor, if there is no delay, every instruction is going to take on an average 1 clock cycle each. 1 into 1 by 2. Okay, that means that 4 by 2.5 into 2 by 1. That means that 8 divided by 2.5. Precisely, if you solve this, 8 divided by 2.5 is equal to 3.2 is the correct option. Now here what we did is, understand carefully. How I came to the conclusion, it is 8 by 2.5. There are a few factors that we need to understand. 4 into 1 by 2.5. This is the number of clock cycles per instruction. This is the number of clock cycles per instruction, right? And what is clock cycle? 1 clock cycle. 1 clock cycle is equal to 2.5 gigahertz, right? T is equal to 1 by F. According to this rule, this 4 into 1.25. It is the pipeline time. What exactly time? Time is equal to 1 by frequency. 1 clock cycle is equal to 1 by 2.5 gigahertz, right? So, the 4 clock cycle. How many clock cycles are required to execute one instruction? In order to execute one instruction, it requires, 1 by 2.5 clock cycles. 4 into 1 by 2.5. 4 is the number of clock cycles required for one instruction. And in a pipeline processor, obviously, generally, if there are no hazards, one clock cycle is expected to be taken by each and every instruction. The clock cycle time is equal to 1/2. So if we solve this, 3.2 is the correct option here. And the next thing is, the next question is on your screen. A processor needs a software interrupt too. This is an important question. This is a fundamental and basic question, but it has a lot of depth in it. First of all, in order to solve this, we need to understand how many types of interrupts we do have. There are 3 types of interrupts. The first one is the external interrupt, second one is internal interrupt, and the third one is a software interrupt. There are 3 different kinds of interrupts: external, internal, and software interrupt. External interrupt: if an external source triggers an interrupt, that falls under external interrupt. It could be your device, any of the devices that are connected to the computer system. It could be keyboard, it could be mouse, or it could be scanner, it could be printer, or it could be timer. If there is an external source connected to your system, that external source will be able to communicate with the system only through the interrupts. All the interrupts, all the signals that are being generated by the external sources to communicate with the computer system are going to trigger external interrupts. And the second one is an internal interrupt. What is an internal interrupt? Internal interrupt will get generated due to the erroneous operation of the computer system. When you try to operate the computer system in an abnormal way, the computer system itself is going to trigger an interrupt which comes into the category of the internal interrupt. For an instance, you are executing a program. In that program, there is a serious error which computer system can never reciprocate to it. What might be that specific error? For an instance, you do have a divided by 0. If you do have a divided by 0 instruction, obviously, generally, the computer system can never understand what instruction is it, rather how to execute that instruction. Generally, I'm a CPU. How will be able to deal with the instruction? In order to do anything, first of all, I should be informed, I should be conveyed. If I have to deal with some task, I'm a CPU, I'm not a human being, I don't have any thinking capabilities. I can't interpret anything on my own. Everything must be fed to me. There has to be some way or the other, I should be able to interpret the instruction. There is a control unit and there is an ALU. There has to be an operation that's only will get carried out if that is explained properly in the language that it is able to understand, right? That I am able to understand. But being a computer system, I don't know how to deal with the divided by 0 because I'm not told with. When I'm not told with, obviously, what will I do? Generally, I would never ever execute this instruction. So I'm going to throw something called an internal interrupt. Whenever there is an erroneous operation which cannot be interpreted by the computer system, obviously it is going to throw an error which in tandem triggers internal interrupt. Fine. Whenever there comes an internal interrupt, the current program will be kicked out. The current program will be sent out to the computer system, sent out of the computer system. But our context is about a software interrupt, which is the third kind of an interrupt. External interrupt from the external sources, internal interrupt due to the errors, software interrupts. Let me tell you something. Write it down predominantly somewhere. Write it down somewhere is a thumb rule. What is the software interrupt? Any instruction of any program, it could be C program or Java program, or it could be any program whatsoever. When you try to execute a program, all the instruction will be divided into 2 different types of instructions. First one is the user instructions. Second one is the privileged instructions. Sir, exactly what is this privileged instruction? Is there any way that we actually can understand a privileged instruction? A privileged instruction is an instruction. Let me tell you. A privileged instruction is an instruction which can only be executed by the CPU itself. A privileged instruction cannot be executed by the user. Privileged instruction or a protected instruction, no matter whatever you call, will only be executed, can only be executed by the CPU. Sir, what is this? Please explain it further. I will. Please listen to me. Let us understand something. There are a few instructions which comes into the category of the IO instructions. What is an IO instruction? An IO instruction is an input and output instruction. Whenever you execute an input and output instruction, IO devices will be accessed. Whenever these IO devices will get accessed, that means that some important resources are in the use. All the IO devices cannot be directly used by the user. If you want to take a printout, you need to take the permission from the computer system, because printer is an exclusive resource of the computer system. User is not allowed to handle the printer directly. When you want to handle the keyboard, you should be able to take the permission from the computer system. This also comes under peripheral device, and a peripheral device can never be directly accessed by the user at all. Sometimes you are executing anything, any of the peripheral devices, when you want to execute, there has to be some service routine executed inside. Now, every time when you want to access one of these peripheral devices, you want to take the permission from the computer system. When you take the permission from the computer system, immediately it will grant you the permission and it will execute the code on behalf of the user. For an instance, let me put it in a very simple words. Let us say there is a printf. During the execution of the printf, what exactly is going to happen? Before the printf, there could be any number of instructions. It could be var a, int a plus b, c is equal to a plus b. All those instructions fall into the category of user instructions. User will be able to execute those instructions. But when it comes to the printf, we are accessing some important system resources. We are going to access the console. We are going to access the screen, which is an important resource of the computer system. You are not allowed to access being a user. For the printf, we're going to take the permission. We're going to request. It means that we are requesting the computer system to execute the printf on behalf of yourself. Whenever printf happens to be executed, this printf will only be executed in the kernel mode, supervisor mode. There are two modes. One is user mode. In the user mode, any user instruction will get executed. Second thing is kernel mode or supervisor mode. The protected instructions such as printf can only be executed in the kernel mode. So here the thing is, whenever there comes computer system interprets the current instruction is the privileged instruction, immediately it is going to switch the mode from the user to kernel. In order to switch the mode from user to kernel, we do require a software interrupt. As simple as that. Simply, in the simple words, a software interrupt is going to change the mode from user to kernel. As simple as this. Okay. So, what is the option here? What is the option? Test the interrupt system of the CPU. This is right away I need to rule out. Implement the core routines. Again, we need to rule out. Obtain the system services which need the execution of the privileged instruction. Yes, privileged instruction will be executed in the kernel mode. So, in order to switch the mode from user to kernel, we do require a software interrupt. Return from subroutines. In order to return from subroutine, we don't require anything. Simple. If you want to simply return from the subroutine, a return statement will be executed, but not the software interrupt. As simple as this. Okay. And yes, it is C. The next question on your screen. Anita Bolishetty, yes. Consider a machine with a byte addressable main memory with 2 power 20 bytes, block size of 16 bytes, and a direct mapped cache having 2 power 12 lines. It is not lines, it is lines. Let the address of two consecutive cache lines in the main memory be E201F hexa, E2020 hexa. What are the tag and cache lines of the address in the hexa for the main memory address E201F? This is F meaning it is E201F. E201. Yes, this is the good question only. There is nothing wrong in it. Yeah. Let us understand a few things in order to solve this. How will we be able to solve this? It's a very simple thing. Already we solved the questions on the cache mapping techniques. Here this question which is on the cache mapping techniques, and whenever you come across this question, first of all you find out what mapping technique it is. Direct mapped cache. It's a direct mapped cache and it's a byte addressable main memory. Let us analyze this. Main memory size is equal to 2 power 20 bytes. Okay, byte addressable. Now the number of address bits is equal to obviously equal to 20. Okay, so in order to represent 2 power 20 byte addressable main memory, we do require a total number of address bits which is equal to 20. And the next thing is, just go to the mapping technique by drawing. Just go to the mapping technique by drawing a block diagram of the number of address bits. This is the total number of address bits here. Okay. How should we divide now? We need to divide this total address bits into two parts. One is index and one more is tag. What is index here? Index is the total number of address digits that are actually required to represent the cache memory. What is the total size of the cache memory? Here we are not provided with the size of the cache memory. We completely are provided with the total number of lines. Total number of lines are equal to 2 power 12. So the number of bits required to represent line for lines is equal to 12. So among 20, the line field is equal to 12 digits, right? And this is not index. Now this will become word field. Okay. What is the word field here? The word field block size is equal to 16 byte. Block size is equal to the word field, right? Block size is equal to 16 bytes. That means that bits in word field is equal to 4. So 12 plus 4 is equal to 16 and the remaining is equal to 4, right? So these 12 bits are for the line and these 4 bits are for the word and the remaining bits are for the tag. So here in the total 20 bits, the first 4 digits are for the tag and the next 12 digits are for the line. Next 4 digits are for the word field. Now when you take a total address of E201F, this is hexadecimal, right? Each digit represents 4 digits. E201F. Now we can clearly divide this way because one digit is equal to 4 digits. Sorry, one alphabet is equal to 4 digits. One alphabet represents 4 digits and the word field is equal to 4 digits. Okay, this is 4 and this 201 is 12 and this one is tag and the tag is equal to E, which is 4 digits, and the line is equal to 201, right, which is equal to 12 digits. Line is equal to 12 digits and the last bit is equal to word field, which is 4 digits. So here in the E201F, 201 is the line, F is the word field. Okay, I hope you got it. What are the tag and cache line address in the hexa for the main memory address E201? E is the tag, 201 is the line field. I hope you got my point, right? E is the tag digit. Did I make it myself clear, Anita? E is equal to the tag digits and 201 is the line field. I hope I made it myself clear. Did you understand this? And once again, let me. Very good. Shall we go to the next question? Yes, we'll go to the next question. Consider a process with a byte addressable memory. Assume that all the registers, including the program counter and the program status word, are of size 2 bytes. This is a very good question. This question is on the stack organization. The stack organization is a beautiful topic in the entire computer architecture and organization because stack is an important data structure for a programmer. I told you how important it is. If you do not have a stack, in order to have this function calls and returns, we have to turn the world upside down being a programmer. It is highly impossible. I can't say it is, highly difficult. I can't say it is impossible. It is highly difficult. In order to achieve this, subroutine calls and returns, we should be able to have a stack in the system. This is on the stack organization. So let us stay focused. Consider a process with a byte addressable memory. Assume that all the registers, including the program counter and the program status word, are of 2 bytes. Every register is equal to 2 bytes. I will tell you. Register size, write it down here, 2 bytes or else 16 bits. Okay, let us have it this way. A stack in the main memory is implemented from the memory location 010016 and it grows upward. Sir, what is this upward stack? Let me tell you. let me tell you this, a very important thing that must be inflicted to you guys. There are two kinds of stacks. One is upward stack, one more is downward stack. For this, I will use this illustrative slide. Okay. Nowadays, all of the programmers, all of the designers are using downward stack. For a downward stack, address range will be started from high end to the low end. Or let us say, a stack is of total of 16 bits, 16 elements. Here, this is the 15th element, this is the 0th element. But stack in origin location is 15. That means that stack will start from 15, goes to 0. That means that it's a downward stack. During a push operation, stack pointer will get decremented. This is the regular scenario. In 2022, you need to understand that most of the designers are using this downward stack mechanism. But what we know in our C programming or Java programming, what actually we come across? As far as the push operation is concerned, one element is pushed into the stack, then stack pointer will get incremented. Did I make myself clear? Stack pointer will get decremented all the time as far as our knowledge is concerned. But let me tell you, that's only one angle of the stack. If the stack is organized as the upward stack, what will happen? Stack pointer will get incremented. And if the stack is organized as a downward stack, stack pointer will get decremented, as simple as this. Stack pointer will get decremented. But the thing is, we don't need to think about downward stack since we've been just provided with the upward stack. We can stick to the basics as what already we know about the stack. There's an upward stack, right? So 2 bytes, a stack in the main memory is implemented from the memory location 0100 and it grows upwards. For that, let me take this help of the illustrative slide. Let me draw the memory. Let us say this is our main memory. In the main memory, stack is starting from 0100. The origin of the stack is 0100. 0100. Okay, from where the stack is being originated. This is the starting location of the stack. And then the current value of the stack pointer is 016E16. For that also, this is the starting location. I would say this is the starting location. This is not where the stack pointer is residing right now. In this stack, there are a few elements. Currently, this is the topmost element. Let us say topmost element, I would say XX. I don't know what is that element. That is the reason why I put XX. And this is where the stack pointer is residing. That means that stack pointer residing at the topmost element, it is pointing at the topmost element. The address of the stack pointer, as we are provided with 016E. 016E. This is the topmost location of the stack where the stack pointer is pointing. The call instruction is of 2 words. Now, that is, so far, this been just pertaining to the stack organization here. That means that so far he explained how the stack is designed. Then this is the actual question we need to answer. The call instruction is of 2 words. The first word is the opcode and the second word is the starting address of the subroutine. One word is equal to 2 bytes. Here the thing is, we already provided with the information. One word is equal to 2 bytes. Let me go to the main memory again. This main memory, one word is equal to, let us say this is one word, right? This is the word. The word size is equal to 2 bytes. 2 bytes meaning it is equal to 16 bits. This is the very reason why each and every register is of 2 bytes. Let me tell you how you are going to design a computer system. When you are designing a computer system, you must be able to take an important parameter into consideration. First of all, you need to know the basics of the main memory. When you look at the main memory, you just look at what is the word size, how a word is being organized. The word is equal to 2 bytes. You come back to the processor and design a register with 16 bits. If the word size is equal to 16 bits in the main memory, the register size must be equal to 16 digits. If the word is equal to 32 bits, the register size must also be equal to 32 bits. So, register size and the main memory location size, both will be one and the same. Okay, but sometimes what may happen is, I mean, there are a few registers which doesn't follow this rule. There are a few registers that does deal with the addresses, main memory addresses, and there are input and output registers. Apart from a few registers, all the registers which are going to hold the data items from the memory will be equal to the size of the memory location. If it is equal to 16 bits or if it is equal to 32 bits, both the register and the main memory locations should be of the same size. Okay. Yeah. The call instruction is implemented as follows. Whenever a call instruction is executed, store the current value of the program counter into the stack. Whenever during the call instruction, we know that every time a subroutine is called, we know that the current program counter value will be pushed into the stack. Right? A routine is calling the subroutine. Before we actually call the subroutine, in order to return back, first of all, we should be able to store the program counter value, right? Where the program counter value is being stored, the program counter value will always be stored into the stack. So during a call instruction, current value of the program counter will be stored into the stack. Okay. Generally, some architectures, during a call instruction, what might happen is the current program status word, the flag register value will also be pushed into the stack. I mean, into the PSW, which is a flag register, will also be pushed into the stack. Now, during every call instruction, we need to understand that two elements will be pushed into the stack. One is the current program counter and one more is PSW. Let me admit a few things very precisely. Generally, there are two things will update the stack. There are a few things. The first thing is the program counter value during a call instruction. Second thing is the PSW, the flag register. This flag, the stack will be updated in two cases, rigorously and continuously. The first one is whenever there is a branch, subroutine call. Second thing is whenever there is an interrupt, service routines call. In these two cases, both program counter value and PSW will be written into the stack. Stack will also be used to store the local variables, which is not necessary to be discussed at this point of period. Load the starting address of the subroutine in the PC. The question is, the contents of the program counter just before the fetch of a call instruction is 5FA016. FO16. After the execution of the call instruction, the value of the stack pointer. Simple. This is out of context. It is an unnecessary information. This can be filtered. Here, finally, the question is, what is the stack pointer? What is the value of the stack pointer? For that, we need to understand what is the instruction currently executing. The currently executing instruction is the call instruction. Whenever call instruction is executed, two elements will be pushed into the stack. One element is program counter, one more element is PSW. Let us go through here. Now it is currently the stack pointer value. Now one instruction is executing. What is that instruction? Call instruction. During the execution of the call instruction, stack will be pushed with the two elements. One is PC, second one is PSW. So here on the top of it, PC will be pushed. On the top of it, PSW will be pushed. So whenever there is a push operation, stack pointer will get incremented. But here, twice the stack, twice the stack has been updated. First time to push the PC, second time to push the PSW. Stack has been pushed for two times. That means that SP is equal to SP plus 2 generally. But here, the memory is word addressable. More importantly, the memory is word addressable and one word is equal to 2 bytes. Sorry. The memory is byte addressable, bigger pardon. Memory is byte addressable. One byte is equal to, sorry, one word is equal to 2 bytes. So generally SP is equal to SP plus 2 since two elements have been pushed. Because since the memory is a byte addressable, in order to update the stack pointer, one updation is equal to plus 2. Two updations will be equal to plus 4. SP is equal to SP plus 4. I hope you got my point. Yes or no? Because byte addressability meaning, I told you already, one location is equal to 16 bits and every byte will be given an address. So this is the first address. First address will have 2 bytes, 0 and 1. Second address is 2. So every displacement of the address will have, will be updated with 2 all that time. So this is the thing. 016E. Let me clear this again. SP is equal to SP plus 4. That is 016E plus 4. I guess 0172E, I guess. 0172 hexa. 0000, 0001, 6 is 0110, E is 1110, 1110. And this is what 016E. I just converted 016E into hexa. We need to add 0100. When you add this, what you would get? This is 0 101 11 01 11 01. Okay, 0111. This is 0111 and 0001 and 0000. So this is 0, this is 1, and this is 7, this is 2. 0172 hexa. 0172 is the correct option here. The next question is as follows, as on your screen. Did I make myself clear? Can I go to the next question? Anita, can I go to the next question? Can you go to the next question, Anita? Fine then. Yes or no? Do we have any doubts in the previous question? Where are all my students today? There's no Anu, there's no Chitra, and there's nobody here. Where exactly are they sleeping here? No, fine. Let us go to this question. This question is, of course, a simple question. It's the design of the ALU. This question is a design of the ALU. The figure shows the design of the ALU, and let us understand actually the how it goes. Consider the following data path of a simple non-pipeline CPU. Registers A, B, A1, A2, MDR. The bus and the ALU are 8-bit wide. Register A, B, A1, A2. This is AB, A1 and A2. The bus and the ALU are 8-bit wide. Total, this is the bus system, right? This is the bus system. Bus is equal to 8 bits. As simple as that. The mux is of a size 8:2:1 and the demux is of a size 8:1:2. Each memory operation takes 2 CPU clock cycles and uses MAR, memory address register, and MDR, memory data register. Stack pointer can be decremented locally. The CPU instruction push R, where R is equal to ARB, where R is equal to ARB, has a specification. R will be transferred to memory of SP and SP will get decremented. How many CPU clock cycles are just needed to execute the push R information? Can I have this question? Can I have this answer from you guys? Can I have this answer from you guys? How many CPU clock cycles are actually needed to execute the push R instruction? Can you answer or you want me to answer? I think I already explained in one of my sessions. You want me to explain or you want to give it a try? This is for you guys. If you want to give it a try, you're welcome. Otherwise, I'm going to explain it for you guys. Okay, fine. I'm explaining. If you, otherwise, at least, just pick it up. You pick it up a random answer. I will say whether it is correct or not. How many CPU clock cycles are needed to execute the push R instruction? Any idea whatsoever? Okay, then fine. Let us not waste any more time. It is 1. No, in fact, indeed, it is not. Let me tell you how it is going to be possible. See, I just want to push R. What is push R? Let me show you my memory register. Memory operation, yes. R, some data will get transferred to memory of SP. That meaning that just, okay, fine. Okay, then. Very good. See, guessing doesn't, have any shortcuts. We need to guess. Otherwise, we can't be able to predict the answer. You can go and have a wild guess. See, if you do not have any answer after having all the possible options, after having all the permutation combinations, obviously we need to go for guesswork, right? Guesswork doesn't have, any shortcomings. Sometimes we need to be able to go to the guesswork. Here, this is the memory transfer. Let us understand that this is the memory transfer. After having read all the content in the question, we can say that it's the memory transfer, memory of SP. From that ALU, information is being transferred to the memory. From the CPU, the information is being transferred to the memory. Okay, in order to transfer this information to the memory, what will happen? Look at the question. Look at the question. Each memory operation takes 2 CPU clock cycles and uses MAR and MDR. For that, let me take the illustrative slide. Let us have a look at the bus system. This is the bus system. This part is, let us say, our CPU. Okay, we do have, the register set and the ALU. This part is main memory. In order to communicate with the main memory, generally any CPU will use 2 registers. Okay, will use 2 registers. One is address register and one more is data register. Initially, let us say I want to send in information to the memory. Initially, CPU will load the address register. Let us say this is 450. Right after which, CPU is going to fill the data register with the content that is going to be needed to be transferred to the main memory. That is, let us say the content is ABCD. That means that in the address of the 450, the content ABCD must be written in the main memory. So CPU always uses address register and a data register. In the same light, in the same context, you must be able to understand as the R is needed to be transferred to the memory of stack pointer. This R must be transferred to the data register, right? Initially, the value that is needed to be sent to the main memory, which is R, needed to be transferred to the data register. Okay, here I would say, in the data register, I am going to load R, where R need to be transferred to the memory location. Now, address register. What address register will have? Address register will have a value from the stack pointer. Now, to the stack pointer, let us say stack pointer is equal to 450. Initially, address register should be loaded with the value of the stack pointer. Now, 450 will be loaded here. That means that to the memory of the stack pointer, we are going to send R. But for that, data register should be filled with the data that is needed to be transferred. Address register is needed to be filled with the address that has to be located in the main memory to where this data has to be transferred. What is the address that we are searching for? What is the address that we are looking for in the main memory? The address is the stack pointer, right? So now, here the thing is, there are initially 2 operations. The first operation is, the data must be transferred to the data register. Address, which is SP must be transferred to the address register. These 2 operations must be performed. Okay, for that, what is the bus system length? The size of the bus system is equal to 8 bits if I'm not wrong. Let us have a look at this bus system size. Have a look at this question. A, B, C, D and the bus and the ALU are 8 bit wide. SP and the MAR are equal to 16 bits registers. Simple, very simple. In order to solve this, we don't need to turn the world upside down. There are only 2 registers which are equal to 16 bits. One is SP is equal to 16 bits. MAR also is equal to 16 bits. Okay, let us say SP needs to be transferred to MAR. In order to transfer SP to MAR, I require 2 clock cycles. Simple, because bus system is of 8 bits, right? At a time, I can only transfer 8 bits. So if you want to make 2 transfers, I require 2 clock cycles. In 2 clock cycles, first clock cycles 8 bits will get transferred. Second clock cycle 8 more bits will get transferred. So SP to MAR will require 2 more clock cycles. Then R must be transferred to the data register. Here for this, in order to transfer R to data register, I don't need anything. Rather, I require only 1 clock cycle. Since all the other register, look at this, data register, any A, B, A1, A2, memory data register, everything is of only 8 bits. Since the bus system is also of 8 bits, I require only 1 clock cycle. So, in order to load MAR and data register, I require 3 clock cycles. Okay. And finally, in order to transfer this total information into the main memory, as given in the question, we do require 2 CPU clock cycles. Altogether, we do require a total of 5 clock cycles. This is the correct option. I hope I made it myself clear. Did I? Or any doubts do you have in this context? Do you have any doubts whatsoever? We require a total of 5 clocks. If you want me to explain it for one more time, I would explain it to you. Otherwise, I will go to the next question. Tell me if you want me to explain it for one more time. Next question is on your screen. Can I go to the next question? Anita, suppose the processor does not have any stack pointer register. Which of the following statements is true? It cannot have the subroutine call instruction. It can have the subroutine call instruction but no nested subroutine calls. Nested subroutine calls are possible but interrupts are not. All sequences of subroutine calls and also the interrupts are possible. This is the final option. What is the correct option? Anita, could you please do your guesswork? Could you please go for a guesswork? I mean, I hope this, you don't even need to go for a guesswork. Simple. Most of the people think that, of course, if we have stack, it is subroutine calls and returns are possible. If we do not have a stack, subroutine calls and returns are not possible. See, if we do not have a stack, also we can use some memory, some CPU registers in order to store the program counter value. If you want to store some program counter value, when you are going to have a subroutine call or return, let me tell you, there are several ways to save the program counter value. The first provision is memory of 0. Whenever there is a subroutine call, there are 3 provisions that we can have in order to store the program counter value. The first provision is, sir, why push R is taking 1 clock cycle? Very good question. This is what I want. Let me tell you this. This Anita asking me about the previous question. Fine, let me solve this. See, stay focused and understand. Let us look at the question. A, B registers, right? A1, A2, again registers. MDR, memory data register. The bus system and the ALU are of 8 bits wide. That means that all these things, A, B are the registers, right? The contents of the registers, any register size is equal to, I will write it here, any register size is equal to, any register, it could be A or B, is equal to 8 bits. Okay. Now the thing is, what is push R? Where R is equal to either contents of A, contents of B. Push R meaning the contents of either register A or B are being pushed into the stack. But for that, what we need to do? Contents of A or B must be transferred to the data register, right? Let us say I am transferring contents of A to the data register, memory data register as given in the question, because I told you already, if you want to communicate with the main memory, we require a data register. If you want to perform a writing into the main memory, we require a data register. First of all, do not think of the main memory. Get the contents that are needed to be written in the main memory. Those contents must be transferred to the memory data register. So, from where the contents are being collected? The contents are being collected from A, must be transferred to the memory data register. Now, what is the size of the A? Size of the A is equal to 8 bits. Right? Size of the memory data register is also equal to 8 bits. And in order to make this transfer, we require the bus system. The bus system is also equal to 8 bits. I hope I made my point very clear. So, altogether, one clock cycle, we can send the contents of A to the memory data register, right? The bus system can accommodate 8 bits at a time. So, in one clock cycle, all the 8 bits will get transferred. But on the other hand, in order to load the address transferring SP to MAR, we require 2 clock cycles because SP is equal to 16 bits. Memory address register is also equal to 16 digits as given in the question. But the problem is the transportation medium, which is the bus system, is just equal to 8 bits. At a time, it cannot accommodate all the 16 bits. At a time, it will only be able to accommodate 8 bits. That means that we do require 2 clock cycles. So, in one attempt, 8 bits will get transferred. In one more attempt, 8 more bits will get transferred. So, in order to transfer SP value to MAR, I require 2 clock cycles. In order to transfer the contents of A to MDR, which is in tandem can be considered as R to MDR, we require 1 clock cycle. 2 is for loading the address into the MAR. 1 is for loading the data into the MDR. Finally, 2 clock cycles are required to, send a word to the main memory as given in the question, right? Did I make myself clear? Any more doubts in this regard? I hope there are no more doubts at all. Yes or no? Did you understand this? Did you understand? I hope you got this point. If you could tell me yes or no, I can move forward. Still, if you do have any doubts, please shoot it here. I will be able to answer. Yeah, suppose a processor does not have any stack pointer register. Which of the following is actually true? As I told you, we don't require to have a stack. Stack can make the thing simple. But if you do not have stack, that is not the end of the world. Even without a stack, we can make this subroutine calls and returns possible. I will tell you how. Let us say this is the main memory. This is the main memory. In the main memory, currently the CPU is executing is 20-second instruction. For the 20-second instruction, there is a program counter value. The next instruction's address is 23 for an instance. Now the current instruction is the call instruction. Call instruction to 56. Since the current instruction is a call instruction, there is a subroutine call. Subroutine's starting address is 56. But before a subroutine call has been made, before the CPU control transfers to the 56th location, 56th address of the main memory, first of all, we should be able to save the program counter value. Unless we save the program counter value, we won't be able to make a return from the called subroutine. So in order to achieve this, first of all, we should be able to store this program counter value somewhere. Generally, we use stack. Generally, we push this, the program counter values whenever we do have, subroutine call. But if you do not have a stack, still there are other provisions. You can use a processor's register. That is, let us say memory of 0. Several other ways are. The first provision is memory of 0. You can transfer the program counter value to the first location of the memory. But here, nested subroutines are not possible. The second possible option, in the absence of the stack, the best possible option is offset, rather origin of the subroutine. I would say origin. The best word to use is, first is memory of 0. Second is origin of the subroutine. Origin of the subroutine. That is, let us say we are at the 23rd location. The 23rd location is the call instruction. Call to 56. Now at that time what we will do is, directly we go to the 56. At the 56th location, in the starting address of the subroutine itself, we are going to save the program counter value. This program counter value will be saved in the starting address of the subroutine. Now this is the second way And the most possible and beautiful way in the absence of the stack, where we can save the program counter value. Of course, here nested subroutine calls are actually possible. Nested subroutine calls are also possible in the other words. But in the first provision, nested subroutine calls are not possible. So that means that there is still some provisions which can make the subroutine calls and return possible in the absence of the stack, right? So all sequences of subroutine calls and also interrupts are possible. Without stack, it is not the end of the programming. Still, the programming paradigm is pretty much possible, right? But only the problem is recursion is not possible. Stack is the only provision that make recursion possible. I hope I made it very clear. So with this, I have come to an end of this wonderful session. But before I go out, and before you people come back to my sessions, I'm going to shortly take a few sessions for the example PYQs. I'm going to come up with some exciting sessions for you, in which I'm going to I'm going to solve a lot of practice questions before actually you go and attend your examination, GATE examination. Before you come back, I want to ask you, I want to give you one homework question. This homework question, which is given in 2007, this question is given in 2007. It's the single data multiple questions. This is the question. I just can either take a screenshot or you can also Google for this question. Consider the following program segment. Here R1, R2, R3 are general purpose registers. Based on this data, there are 3 questions. I want you people to answer me whenever you people come back. As simple as this. Whenever you people come back. But without trying, I just don't want you people even to go for sleep. This is what I exactly want you from, guys. I guess in one of my previous session, I explained you this. Even without, if you, say that, sir, I'm not able to solve this, I'm going to solve it for you guys whenever I come back for the example questions, right? So this is your homework. Let me tell you. Solve this question precisely and solve all these kind of questions where the program is given, some machine language program is given, and some details related to the machine language program that has been given. And then based on the details, you will be asked a few questions. And in addition to which, there is one more question that I want to ask you people. During a halt instruction, how the program counter value is going to get updated? I want you people to come up with the answers for this whenever we come back again. And at the same time, if you already solve it, and if it is like, if I take some days to meet you people again, use our Telegram account. You know my Telegram channel. In the Telegram channel, you shoot the answers. Okay. So that's it from the session. Anil Sir signing off. Any more doubts? You ask me. Otherwise, let me sign off from this wonderful session. I'm going to meet you people again with some exciting content, and I'm going to come up with some example and practice questions, rigorous questions. Okay. So that's it from my side. Anil Sir signing off, and good night.